Okay, so this is the outline for chapter 39. The first part of the chapter 39, we will not talk about all the content for the chapter 39. Yeah. Actually, we will talk about the energy of a trapped electron, trapped in infinite square well and also the finite square well. And we will also introduce the wave function of a trapped electron and an electron in the finite well. Okay, so here the energy of a trapped electron. So it says the states or discrete standing wave pattern in which the string can oscillate are those for the width for which the length L of the string is equal to an integer number of half wavelength. That is, the string can occupy only state for which L equals this n lambda over 2. So if you know how to play some instrument like a piano or guitar or whatever musical instrument, especially with a string, there are different key, the key actually depends on the material, but also the length of the string. So if you need a higher key, then the string should be shorter, and if you need a lower key, then you need a longer string or make it loose. So actually, the fundamental frequency or the lambda depends on the length of the string. Like, so if you try to fix a string here, then if you try to play some sound from it, you try to use the finger to play it, and then the wavelength may be like half wavelength will be something like this, and then C, maybe V equals F lambda, not necessarily a EM wave, maybe for other wave. The speed of the wave equals the frequency multiplied by the wavelength. So if the wavelength, this one should be the longest one, and which means that this is the fundamental frequency this string can play. And also if it is something like this is the wavelength. And then maybe it can be something like this. So this is 3 times. To it. So which is like if the length of the string is fixed, then it is like the lambda should be something like this. The total length, half of it, 1/3 of it, a quarter of it, so on and so forth. But yeah, if you just like to put the wavelength to be a fixed number, then it is like a half wavelength multiplied by a constant, multiplied by integer, to be the length of the string. So in quantum mechanics, this number n is so-called the quantum numbers. And here we can imagine the case like if we have 3 segments. In chapter 38, when we learn the tunneling effect, we have V equals 0 on the left one and the right one, and then we have a negative voltage in between, so that it has a potential wall in between. But here it is not the case. We make the potential to be 0 in the middle part, and then for the left and the right part, we make the potential or potential, electric potential to be negative infinity. Although you know it is not possible because you need infinite many energy to make this. However, in mathematics we can assume the V to be negative infinity, which will simplify the calculation. Which will simplify the calculation. So you just accept, the mathematic model can be like this. So if we have V to be negative infinity for this part and also this part, which means that the potential, the electric potential is infinity. Because here we also assume it is an electron, so it has a negative charge. So U equals QV, so it has a positive infinity electric potential energy there. So this is called the infinite potential well, infinite potential well. So in Chinese it is called 无限生对称量子井就一个很长的名字。So the elements of an idealized so 理想的trap designed to confine an electron to the concentric cylinder. We take the semi-infinite long end cylinder to be an infinite great negative potential and the central cylinder to be zero potential. Actually, this line also should be infinitely long because otherwise, if it is not infinitely long, then this electron may not be trapped there, may be able to go through this wall according to the tunneling effect. Of course, if it is infinitely large, then it is not still possible to go through it, but practically if it is not infinitely large, then the trapped electron may still be able to come out from this well. 所以量子电脑的话，我们需要一些做量子计算的话，你就要把一个很小的量子困在一个很小的地方，它才能帮你计算。所以这个是这么用。Okay, so just mention if you have a string here for classical mechanics point of view, and if this length is fixed, then it should be something like sine of something. So here we should be able to have the wave will be like, this is the amplitude times sine of n pi over Lx, So if it is n equals to 1, which is the fundamental frequency, which is like pi over Lx, which means that if x is 0, sine of x is 0. So it is always 0 here. And if x is L, which is the right side of this well, when you plug in L here, sine of n pi L over L and L cancel. Sine of n pi, if n is integer, sine of n pi is also always 0 because the u here is infinitely large. U is here infinitely large. So the wave function for the electron in this region and this region should be 0. The potential there is infinitely large. The electron can never be in that region because the potential is too large. And if you still remember, for the boundary condition, the wave function should be continuous at the boundary, and also the first derivative also continuous at the boundary. So you know this point should be 0. This point should also be 0, which means that this one should be a solution to the Schrödinger's equation, and then it satisfies all the things. Okay, so we know if we plug in L to be 0 or L, then this one should be 0. And if you take the derivative and then blah blah blah, you can still find that this one is also continuous. Maybe not continuous, because yeah, this is two straight things there. Yeah, it can never be. The first derivative is not is not continuous at this case. So we see that for all value of n, for all time, there is a 0.0 displacement at x to be 0 and x to be L, capital L, as there must be, because the wave function should be continuous at least. So the electric potential energy Ux of an electron confined to the central cylinder of the ideal trap, we see that U equals 0 for the middle part, and then U tends to infinity for the left and the right part. Okay, so the next thing is that because the electron is non-relativistic, we assume the electron is slow enough to ignore the relativistic effect. So this momentum magnitude P is related to the kinetic energy. So K is if you still remember, K is P squared over 2m. P is K squared over 2m. So if you move this term over and then take the square root on both sides, so P is square root of 2mk. So where m is the mass of the electron, yeah, K is the kinetic energy. And then also we have the de Broglie relation, which means that lambda equals h over p, or p equals h over lambda. And then p equals this one, so we plug it here. We have a lambda equals h over square root of 2mk. Yeah, so so here we have some interesting things. Is that the energy of the particle for different quantum number is like this: h squared over 8ml squared. Yeah, like this. H squared over 2, yeah. Yeah, let me see how to come up with this one. Actually you should have something like K equals, and actually E equals to K equals to P squared over 2m, and P is actually h over lambda, so it should be something like h squared over 2m lambda squared. 2m lambda squared. Yes, be something like this. And let's see. This is the frequency. So the wavelength of it will be like the lambda n will be something like L over 2L over n, because for the longest one we have the wave like this. So the total wavelength is 2 times L when n is 1, and then for n is 2, it is something like this. So L is the wavelength, so 2L over 2. So lambda should be 2L over n. Lambda n is 2L over n. Lambda n. Okay, so if we plug in this one here, we will have h squared over 2m, and then lambda squared will be 4L squared over n squared. This is h. This is h, not h bar. This is h. So finally, we will get 8ml squared in the denominator, and then in the numerator we have a h squared n squared. Actually, if we use the h bar to write this out, we will have something like h bar square n square 2m pi square. No, pi square on the top, something like this. Yeah, this one and this one is, yeah, I think it is equally complicated, so I just leave it like this here. So actually this is the energy. This is the energy for the particle if it is trapped in this infinite square well. In this infinite square well. Yeah, maybe you will ask why this is the solution. If you don't believe, you can try to plug this one in the Schrödinger's equation, and it should satisfy. It should satisfy. Or in the other way around, if you want to do it more elegantly, you can try to solve it by yourself. Okay, so this is the energy. You can see that h square is the constant. H is the Planck constant. This is a constant. 8 is a number which is also a constant. M is a constant related to the particle, which is the mass of the electron in this case. L is the width of this well. So in this case, if this setting doesn't change, this is a constant. This is a constant. And n is related to the state, 是量子数啊。所以就是 so it is like the energy is like a constant. This is a big constant multiplied by n squared. So if n is larger, the energy is inverse proportional to the square of the quantum number. And one thing we can point out is that actually we will call this one the ground state. We will call this one the ground state. E1 is the ground state. And the second state, we'll call it the first excited state. 第一个激发态，这个是基态，然后第一个激发态，第二个激发态，如此类推。So this is the ground state, first, second state for the E2, second excited state for the E3, so on and so forth. And of course, it increases proportionally to the square of the quantum number. So the difference between the adjacent two states become larger and larger for higher state. So these are the lowest 5 energy level allow the electron. No intermediate level are allowed. Because we have the infinite wall here, and actually the wave function must be 0 at the boundary, so there shouldn't be any intermediate energy for the electron to occur there. So it can be either have this energy at the ground state, and if it can absorb some energy from the outside, maybe from some EM wave, then it can absorb some energy to jump up to a higher level, and then it may jump down, and then it emits some EM wave, and then jump back to the ground state, something like that. So several of the allowed energy given, and then for the infinite well here, the width is L equals 100 picometers. Such a plot is called the energy level diagram. And here it also mentioned that the electron is excited to a higher energy level. It may absorb some energy, and then it may jump up from E1 to E4. But actually, you need to care about is that the delta E. If it needs to jump from E1 to E4, it needs to absorb exactly the same amount of this energy, this delta E, which is E4 minus E1. You can just plug in the values here. You can find this constant, and then E4, which is 4 square minus 1 square, and then multiply by this constant, which is the energy required to jump from E1 to E4. And it should absorb the wave with exactly this frequency to obtain this energy difference. To obtain this energy difference. So if a confined electron emits a photon, the energy HF of this photon must be equal to the energy difference delta E between the initial energy level of the electron and a lower level. So if we need to jump up, it should absorb this energy with this frequency. And if we jump down from E4 to E1, it will still emit the EM wave with this frequency. And possibly it may jump down from E4 to E1 directly, but it may jump from E4 to E3 first to emit this is delta E43. Maybe I was write like this, which is HF43, something like this, and then it jumped down again from E3 to E1. So it will emit the EM wave with the frequency HF31, something like this. Or it may jump from E4 to E2 and then from E2 to E1. But the EM wave it emits with a different frequency. Or it may also jump from E4 to E3, from E3 to E2, from E2 to E1. Any combination is possible here. So let's see an example here. So it says an electron is confined to one dimension, infinitely potential energy, well of width L equals 100 picometer. So what is the smallest amount of energy of the electron can have? Okay, so here, so first of all, we can simply find h squared over 8 ml squared. So we just plug in the value 6.63 times 10 to minus 34 quantity square over 8 times 9.11 times 10 to minus 31 times 100 picometer, which is 100 times 10 to minus 12 quantity square. So this number is nothing but 6.031 times 10 to minus 19 joule, like this. So this is the constant we always use, which is like, this is actually the E1. When we plug in n equals to 1, then it is E1. So E1 is nothing but this one, x squared over 8 ml squared times 1 squared. So this is 6.031 times 10 to minus 18 joule, or in EV it is 37.7 EV. Okay. So what is the smallest amount of energy the electron can have? Yeah, so this is the ground state, which is actually the smallest amount the energy of the electron can have. So this is the answer. And then for the second one, how much energy must be transferred to the electron if it is to make a quantum jump from the ground state to the second excited state? The second excited state means E3. Okay, so here we have E3 minus E1, which will be h squared over 8 ml squared, and then 3 squared minus 1 squared. Okay, so this is nothing but 6.031 times 10 to minus 18, and then times 8. So this value is nothing but 4.83 times 10 to minus 17 joule, or in EV it is 301 EV. So this is the required energy for the electron jumping from the ground state to the second excited state. And then for C, if the electron gains energy from jumping the energy level from E1 to E3 by absorbing light, what light wavelength is required? So actually lambda equals C over F because it is absorbing the light. So we should use the speed of light here, and actually F equals, we keep in mind that delta E equals HF. So which means we have F equals delta E over H. So we have here HC over delta E, because F is in the denominator. We have delta E here, H, put it on the top. So we have HC over delta E here. So we plug in the value. So we have a 6.63 times 10 to minus 34, which is a Planck constant, times speed of light 2.998 times 10 to the 8th power, all over this delta E. This delta E is here, 4.83 times 10 to minus 17. So this one is a 4.12 nanometer. 4.12 nanometer, which is quite short, which means it is a high energy photon. For visible light, the wavelength is around hundreds of nanometer for visible light. So this is much shorter than the visible light. Okay, so once the electron has been excited to the second excited state, what wavelength of the light can be limited by the excitation? So it is actually at the E3, and then it may jump back to E1 directly. This is the first possible case. And then the second possible case is it jump down to E2 and then jump down from E2 to E1. So it will altogether generate three wavelengths of frequency of the light. So the first one will be lambda 31. It jumped down from E3 to E1 directly. So which is nothing but 4.12 nanometer, which is what we have calculated here, because it absorbs this wavelength jumping from E1 to E3. So when it jumps down from E3 to E1, it will emit the same light with the same wavelength. So the second one will be lambda 32, which is HC over E3 minus E2. So H is still 6.63 times 10 to minus 34 times 2.998 times 10 to the 8th power, and then all over this one is 6.031 times 10 to minus 18, which is the big term there. The big term here, x squared over 8ml squared, which is this 6.031 times 10 to minus 18. And then 3 squared minus 2 squared, because it's jumped down from E3 to E2. So this number is 6.6 nanometer, which is a bit longer than the first one, because the energy is smaller, because it's jumped down from E3 to E2. The energy to emit should be smaller here. And then the third case is lambda 21, which is nothing but HC over E2 minus E1. So we should have the same thing here, 6.63 times 10 to minus 34, and then times 2.998 times 10 to the 8th power, all over 6.031 times 10 to minus 18, 2 squared minus 1 squared. So the answer will be 11 nanometer, even longer than the second one, because the difference between E2 and E1 is smaller than the energy difference between E2 and E3. Okay, actually, we can find this solution by solving the Schrödinger's equation. We have the Schrödinger's equation here. This is the time-independent Schrödinger's equation, and then with the potential defined at like 0 between 0 and capital L and infinity elsewhere. So the wave function for the electron are given by this one. Okay. So actually, you don't actually need to solve the potential the wave function for region 1 and region 3 because phi 1 and phi 3 should be zero for x is smaller than 0 and x is larger than capital L or equal, like this. The only thing we need to solve is the middle part, the region 2. And here we have u to be 0. So the only thing is that we have d square phi dx2 plus 8 pi square m e over h squared phi to be 0. So we only make u to be 0 here, and this is the whole term. And then we can make k to be the square root of this one, 2 square root of 2 pi square root of me and then over h. Wow, very complicated. Like this. So this one will be like d2 phi dx squared plus k squared phi to be 0. And then you will see that phi to be a cosine kx plus b sine of kx. K is actually this one. And finally, we will be able to find that k is actually n pi over L. K is actually n pi over L, rather than these complicated things. And also, when we substitute the boundary condition, we know that this term should also be 0. So finally, we get this term with k to be like that. And of course, if you just try to equalize these two things, you should have a square root of 8 pi square me like this over h, which is the square root of this one. I don't try to write it like this, equals n pi. Oh, actually, it should be an L here, because we try to plug in L here. So this one should be the whole thing. Should be n pi. Or maybe we can just make this one equals to n pi over L, because this is K, this is also K, so this one should be equal to this one. And then you can find that this is actually H here. So you can try to square on both sides, and then we have 8 pi square me over h square equals n square pi square over l square. And then we can cancel this pi square, and then we can just move this term to the right side. Then we'll be able to find that E equals n square h square over 8m l square, which is what the textbook tells you, although it has not tell you why it comes from. Actually, all the equations should be derivable, I think, in the textbook. So actually, this is the wave function. This is the wave function for the infinite square well or infinite potential well. And if you still remember the probability density function, is the absolute value of the square of the wave function. I should say the square of the absolute value of the wave function. So, and in the textbook it tells you that this one is the probability density function. So you need to multiply by dx or integrating from somewhere to another place to find the probability. Because if you have not learned the probability, you may not accept the probability density function easily. So, but in high school you should have learned probability. So actually you should integrate the probability density function for some range to get a probability, then it may be easier to understand. So this is the probability that the electron may be occurred at this dx range. So px, this is the probability, which is the probability density function multiplied by the width of this length. So which is like, this is the probability density function, which is nothing but the square because it is a real function. So this is just a square of it. So now we can see that if the L is 1, taking the square is something similar. And originally, for the phi, if n is 2, it should be something like this. So taking the square, it will be something like this. The frequency is double because you see sine square of x is 1 minus 2 sine should be something like a sine square of x. Sine square of x is it should be something like 1 minus cosine of 2x over 2. Yeah, something like this. Yeah. So the frequency, after taking this square, the frequency is double. Of course, it is shifting a bit upward. So you can see the probability density function for n equals 2 is like this, for n equals 3 is like this, n equals 15 like this. So for n equals 1, so it is like the electron will be occurred closer to the middle part, which is something like if you have a room and you don't really like to moving continuously, maybe you will not like to leaning towards the wall. Maybe you will feel like you stay in the middle part of the room rather than going to the wall, because for some reason maybe you hit the wall, you will feel painful, then you will not like to be close to the wall. So the probability density function may be higher, should be higher when n equals 1, near the middle part of the well. But if n is large enough, which is something like the particle might be something like it can be go over the whole well, because even though some of it is lower, some place of it is lower, but it is like the electron can be go maybe to here, to here, to here, to here, or up to here. Somehow like equally probable. Yeah, so maybe let's stop here today.